Hello everyone, myself Ronak Kumar, and today we are going to discuss a very important reaction in organic chemistry, that is electrophilic aromatic substitution. It's a very important topic of class 11th. Every year we see some questions are asked based on this topic. So let's start. So let's first understand what's the meaning of this word electrophilic, then we'll understand the meaning of aromatic, then we'll understand the meaning of substitution, and then we'll go ahead and study this whole electrophilic aromatic substitution reactions. Okay. So let's first start what is electrophilic. So before understanding electrophilic, we have to understand what is an electrophile. So let's understand first electrophile. So what is an electrophile? So electrophile is a reactive species. We represent it as E plus. What this reactive species is? This reactive species is an electron loving species. So if we try to understand the word here, this electro means electron and phile means loving. So those type of reactive species which loves electron, they are known as electrophile. And on the other hand, we have other reactive species that is known as nucleophile. So what is nucleophile? If you look at this word is nucleo. Nucleo means nucleus and phile means loving. So nucleophiles are nucleus loving species, and in nucleus what we see? In nucleus we have protons and neutrons. So nucleophile are nucleus loving species, which means they are proton loving species. Okay, now let's come back to electrophile. See, electrophile are electron loving species. So we have electron loving species. So if there is a center which is electron rich, or let's say this is an electron rich center. So if you have electron rich center, and one of the center you have is electron deficient, because why? Because it needs some electron, because you have a positive charge developed on this species. On this species you have a positive charge, so it's electron deficient, and now this center is electron rich. So what will happen? It will try to interact with this. It will interact with electron rich species. So the flow of electron will take place from electron rich center to electron deficient center. Okay, good. So we have understood what is an electrophile, and the attack of an electrophile is known as electrophilic. So this is how. Good. So electrophile you have understood. Now let's understood aromatic. So when you were studying organic chemistry, basics of organic chemistry, you might have come across this word aromatic. So let me also explain what is aromatic. So in organic chemistry, we can classify some compounds as aromatic, non-aromatic, anti-aromatic based on some conditions. What are the conditions? The conditions are, if you want to classify an organic molecule to be an aromatic molecule, there are three conditions. This is known as aromaticity conditions. We can write. Okay. So what are the aromaticity conditions? The first condition is molecule should be planar. Molecule should be planar and cyclic. So the molecule should be planar and cyclic. And the second condition is there should be delocalization of electron. There should be delocalization of electrons, correct? What is delocalization? Delocalization means electrons are not localized at a point. They are delocalized, means they are spread out. Okay. So there should be delocalization of electron. This is the second condition. And the third condition we have is you have 4n plus 2 pi electrons. So if you are looking at the cyclic system, if your molecule is planar and it's cyclic, and if there is delocalization of electrons in this molecule, and if you count the number of pi electrons, if it is coming in this numbers 4n plus 2, for example, n can be 0, 1, 2, 3. So for n0 you have 2 electrons, for n1 you have 6 electrons, for n2 you have 10 electrons. So if you are having this number of pi electrons, 2, 6, 10, then you will say, the molecule is an aromatic molecule. Okay. For example, we can look. I can give some examples of aromatic molecule. These are the conditions which you have to remember. The molecule should be planar, there should be delocalization of electron, and there should be 4n plus 2 pi number of electrons. Okay, let's take the example of this benzene. This benzene, if you look at the hybridization of each carbon is sp2 hybridized. Each carbon is, all carbons are identical here, and each carbon is sp2 hybridized, and we know the geometry of sp2 hybridization is, it's a trigonal planar geometry. Okay, so if you look at the geometry of this benzene, you will find that it's planar, correct, and the second one is cyclic. So the first condition is fulfilled. Okay, now if you look at the structure of benzene, what you will observe that benzene has a pi cloud. So what you will observe that the hybridization is sp2. So hybridization is sp2. What it means? It means that only two of the p orbitals are coming and mixing together to give sp2 hybridization. So one of the p orbital is left unhybridized. So these are the p orbitals which are left unhybridized. So we can mark it like this. Now you will see that there is a delocalization of electron. What does it mean? It means that you have an electron cloud over the benzene. This is the benzene, and you have an electron cloud over this, and you have electron cloud over this because of the pi overlap of the orbitals, of the unhybridized orbitals. So you have a benzene. I can show you with this example. You have this benzene. Let's assume this is the planar benzene molecule. You have an electron cloud over the benzene. You have an electron cloud down the benzene. So what is there? It's actually a delocalization of electrons. So electrons are spread out throughout this benzene. It's not localized at one position. Okay. So the second condition, delocalization, is also fulfilled. So two conditions are already fulfilled here. You have a planar geometry, you have a cyclic geometry, you have the delocalization of electrons, okay, and the third is you should have 4n plus 2 pi electrons. Okay, so when these all three conditions are met, we say that the molecule is aromatic. And why this classification is done? Because some molecules are more stable than other molecules. So these aromatic molecules are more stable than compared to the non-aromatic or anti-aromatic molecules. So that's why we study this type of molecules under topic known as aromatic reactions or aromatic molecule based reactions, or we say specifically if we are studying this reaction, we are saying electrophilic aromatic substitution. So here this aromaticity I have just explained. So aromaticity, for these are the conditions: planar, delocalization, 4n plus 2 pi electrons. Okay, so you have understood. One more example we can take. Let's see. If you have this molecule, look at this molecule. This molecule is planar. No, it's not planar. So let's put a carbocation here. No, it's planar. Yeah, it's planar. So if you see, the hybridization of each carbon is sp2. Now you see you have cyclic planar geometry, okay, but you have not fulfilling the third condition, which is 4n plus 2 pi electrons. So here you have only 4 pi electrons, 2 to 4. But in benzene you have 6 pi electrons. So what are the conditions? 0, for n is equal to 0, you should have 2, 6, 10, this number of pi electrons. Look, 2, 4, 6 pi electrons, this condition is satisfied here. But this condition is not satisfied here. So this is not aromatic. This is actually not aromatic, so we can write, but this is an anti-aromatic molecule. This is when you are studying the organic chemistry, basics in organic chemistry, might have studied that this molecule is an anti-aromatic because this is having a 4 n pi electrons. Okay. The other molecule which I can show, this is a carbon ion at the center. This molecule is an aromatic. If you'll see, this will satisfy all these three conditions. So this is an aromatic molecule. Okay, good. So we have understood what is electrophile, we have understood what is aromatic. Now it's time to understand what is substitution reaction. Okay. In organic chemistry, we have different type of reactions like addition reaction, substitution reaction, elimination reactions. But here we will focus our study on substitution reaction. So let me write a very general reaction. So we have a molecule Rx, we have another reactive species Y, and the product what we are getting, this Y is substituting X and coming in place of X, and it is bonding as Ry, and X is leaving this R as a leaving group. So what we can, this is a general representation of an of a substitution reaction, where we can see that this Y is substituting X. So Y is coming in place of X and it is forming RY compound, and your X is leaving. So this is a general substitution reaction. Okay, we have a different type of reactions, like I told you just that it can be addition, it can be substitution, it can be elimination. So there are different class of organic reactions. So here I have explained that how substitution reaction will take place. So you have a Y will substitute X, Y will come in place of X and it will bond as RY. Okay, so this is a general substitution reaction. Okay, thank you. Now we are going to study one of the very important electrophilic aromatic substitution reaction. One of that reaction is known as nitration. So I will give the title nitration of benzene. Okay, so benzene we have seen it's an aromatic molecule. So all these three conditions will be satisfied. Now we are going to study nitration of benzene. It's the first organic electrophilic aromatic substitution reaction which we will study. So what are the reagents we'll take and what are the substrate we'll take? The substrate will be benzene. Of course, you are doing your reaction on benzene, so you will take the substrate benzene, and you will take concentrated HNO3, and this will be concentrated, and this will be also concentrated H2SO4, and these are the reagent. You will take benzene, you will take concentrated HNO3, you will take concentrated H2SO4, and what will be the product? So you will get nitrobenzene. So what you are getting actually, you are getting a nitrobenzene product. So this is called nitration reaction. So this is a very simple reaction. It looks like a very simple reaction, but the reaction is not very simple. If you look at the mechanism, it involves multi-step reaction. So this is benzene. You are nitrating this benzene using this concentrated HNO3 and H2SO4. Okay. So now let's look at the mechanism. This general reaction I have written here. So now we'll look at the mechanism, how this reaction is proceeding. This is actually a two-step reaction, where we'll first let's understand how this nitro group is first forming. So first we'll understand this general reaction. I should write here. So your electrophile is nitro. So this is your electrophile, and this will give your nitrobenzene. Okay, good. So now let's first understand how this electrophile is getting generated. So we have two acids we have taken. What are the acids we have taken? We will draw the structure. We have taken HNO3. So this is O, this is H, and this is double bond O, this is coordinated bond O. So this is our HNO3 molecule. Okay. And what is the other acid we have taken? We have taken the other acid as H2SO4. O, this is H, S, double bond O, O, H. Now we know that between this nitric acid and sulfuric acid, which one is a stronger acid? So obviously sulfuric acid is a stronger acid. So now what it will do, this oxygen will get protonated by the hydrogen of sulfuric acid, because sulfuric acid is a stronger acid. So in this case, what we are observing, that this sulfuric acid is acting as an acid, but this nitric acid is acting as a base. So we have seen the definition of an acid and a base according to Lewis acid-base model. So proton acceptor is a base and proton donor is an acid. So it is acting as an acid, and this nitric acid is acting as a base. Okay. Now what will happen? After this protonation, this is N double bond O, you have two protons, this, and this is a very unstable system. This is a very unstable species, where you can see you have a protonated oxygen. So you know that oxygen is already an electronegative atom, and a positive charge on electronegative atom is going to make it more unstable. Okay. So what will happen? This will go under elimination of water. What do you mean? That it will get water will come out from this species, and it will generate an electrophile NO2 plus. So first in this case, what will happen? You will have an electrophile generation. So electrophile will generate like this. You have a nitric acid, you have taken sulfuric acid. Because sulfuric acid is more stronger acid than compared to nitric acid, so you have an electrophile generation like this. Okay, so you have your electrophile here. Now from here, now you see you have an electrophilic center. Okay, So electrophilic center, this is electrophilic center. Now let's understand what's the nature of this electrophile. Look, there is a positive charge. So it's already an electron deficient center is present here. Okay. And you look at benzene. Benzene, we have discussed that benzene is having a electron rich center because it is having a pi clone. Okay. So this is electron rich center, this is electron deficient center. Now the reaction this we have studied is the generation of electrophile, how this electrophile is getting generated. Now we'll look at how this electrophile is interacting with this benzene. So we have benzene. Okay. Now you have taken your electrophile. Now you see what will happen. You have a benzene system, you have electrophile, so this is electron rich system, this is electron deficient center. Now what will happen? This one of the bond will interact because you have a pi axis cloud here, so you have electron axis here. So it can attack like this, and this is a slow step, and this is rate determining step. Okay. So what will happen? This will go like this. You have NO2. Here you have hydrogen. Okay. Sorry. Yes. Here you have hydrogen, and here you have a carbocation. Okay. Good. So this is how. This will be the intermediate which will be formed. So this is intermediate which will be formed. Okay. Now you see. This is the slowest step, and you have a benzene. You have electrophile nitro group, and which is interacting with this benzene system. So electron will flow from benzene to nitro, and this intermediate you will be getting. Okay. Now what will happen? You see aromaticity has lost here. Benzene was earlier aromatic compound, but now this compound is not an aromatic. So aromaticity has lost. So this is the driving force attack of this nitro. So what's the next driving force for this molecule to go ahead is the gain of aromaticity, because we know that aromatic compounds are stable compounds compared to this type of system. This system versus the upcoming system will be more stable because it's an aromatic. So what will happen? Now this hydrogen will be lost to regain the aromaticity. So what it will look like? So the aromaticity will be regained, and you have your nitrobenzene. Okay. So this is your nitrobenzene. So this is your nitrobenzene. There are other type of electrophilic aromatic substitutions also. So we have studied nitrase, and the other reaction we can also say this is another reaction is sulfonation. So if I write the general reaction of sulfonation, so how it will look like? You have a benzene, and you will take concentrated H2SO4 and SO3H will add. Okay, so this is how your sulfonation will take place. So if I explain the mechanism here, I hope this nitration is clear to you. So the first is generation of electrophile. So first try to understand how the electrophile will be generated. So you have OH, this is H2SO4. So one molecule of H2SO4 will protonate from the hydrogen coming from the other sulfuric acid molecule. So what will happen? This, let's say, is going to protonate. So it's going to abstract. So this will form your nuclear. This will form your electrophile. So it will give H double bond O, O, and you have H, 2 protons, OH. Now once again water will leave because water is a very good living group. So it will form H double bond O, OH, positive charge here. So this is your electrophile. Now the same process will happen. This benzene, one bond will interact with the center, and once again the aromaticity will be lost, aromaticity will be gained, and you will get the sulfonated product, that is SO3H will be attached to a center of benzene. Okay. Good. Now this is sulfonation, which you have understood. Now one more important one is Friedel-Crafts alkylation and Friedel-Crafts acylation, which I will discuss here. So one reaction is Friedel-Crafts alkylation. So look, Fiddlecraft of alkylation, we see here, this alkylation is actually, it's saying that you have some alkyl group coming and attaching with this benzene. Okay, so what's the general reaction? The general reaction is you will take benzene, okay, and you will take some alkyl group with chlorine attached to it. So it will be, you will be taking an alkyl chloride or any other alkyl group attached to some halogen like chlorine, bromine, and you will take a Lewis acid like AlCl3, FeCl3, AlBr3, this type of Lewis acid. Why these Lewis acids we are taking? Because to activate this reactant, activate this reagent we are taking. So how this reaction will go ahead? So it will form toluene. So this is your toluene. Okay, now let's understand the mechanism. This is the general reaction which I have written here. So the mechanism will go like this. Your CH3Cl and AlCl3 will react. This Cl bond will go to AlCl3 and it will form AlCl4 minus, and you will get your CH3 electrophile. This is your electrophile. This is your Lewis. This is your Lewis acid. This is forming AlCl4 minus after reacting with CH3Cl. Okay, and you are getting your electrophile. Once again, the same process will happen, and you will have your benzene. So this bond will go ahead and interact with this CH3 hydrogen. You have two bonds here with positive charge here, and once again the regain of aromaticity will take place, hydrogen loss will take place, and you will get your benzene with methyl group attached to a carbon. Okay, so this is your toluene, this is how your alkylation will take place. The other reaction which we are going to discuss is acylation. So acylation is actually this group is known as acyl group. So this group is your acyl group. So this is your acyl group. So Fiddlecraft alkylation, we have alkylated the benzene. Now we are going to acylate the benzene. So how the general reaction look like, I'll just explain here. You will take one reagent as acyl chloride, and you will take once again the same Lewis acid, FeCl3, AlCl3. These are Lewis acid. Why this Lewis acid we are taking? We are taking this Lewis acid to activate this acyl group. Okay, so once again the reaction will be very similar to it. So you will get an acyl chloride. This will react with your aluminum chloride, and you will get your this is acetophenone. Oh, good. So let's understand the mechanism, how the mechanism will go ahead. So first electrophile generation will take place. So electrophile generation, okay. So what will happen? This CH3COCl react with AlCl3. So you have CH3COCl plus AlCl3. It will react to give you CH3C double positive charge plus Cl minus. Okay. Once again, you got your this positive charge here. It can be in resonance. You have protons here, so it can be in resonance. So you can write resonating structure like this. Triple bond O. You have a positive charge on oxygen. So once again the same thing will happen. This benzene will interact, one bond will go and interact, aromaticity will be lost, regain of aromaticity will lead to give the product as this. So this acetophenone will be the Fiddlecraft acylated product. Okay. Hope you have understood the basics of electrophilic aromatic substitution and some of the reactions which I have studied like nitration, sulfonation, Fiddlecraft alkylation and Fiddlecraft acylation. So okay, that's all for today. Thank you.